more geometry into your math circle sessions and in what ways you can do it. And I'm not going to be specific about the age of the students. I'm going to talk about math circles from elementary age to high school age, and of course the strategies there are different and the topics are different and the problems are different, but we'll try to see all of those. So the setting in which I usually see this is the following. It's the Los Angeles Math Circle. So we currently have 4 groups. We have Junior Math Circle, which has students in grades K through 4. We have one lead instructor who runs the session, and then we have kids sitting at tables arranged strategically so that older kids are with older kids, typically younger with younger kids, and they sit with the same group each time. So this also creates a certain social context for them, but also the goals that we have for those children within the large age span are different. For the oldest, the goal is to not only solve all the problems as much as they can, but also present their solutions carefully and write things down as much as possible. For the youngest, it might be just getting the taste of what this topic is about, hearing something new, but actually our kindergartners are just two kindergartners, they're both very strong, so we don't have problem dealing with that. So the 2 group A's, not a very good name, but I'll try to come up with something more creative by next year, have grades 4 through 6 loosely and 5 through 8. So this is mostly the group that was there last year, and this is the group that started this year. So they're, in the age they're almost the same, but in terms of experience they're different. And to some extent this group repeats what this group was doing last year. Also, while trying to improve the handouts and the materials, there is always room for improvement. And of course, bring in new topics. So they also, each of the groups again has an instructor and several assistants, although as kids get older, the number of assistants decrease. My assistants are usually graduate students and sometimes outstanding undergraduate students. So I'm very lucky to have them because I'm at UCLA. And then in group B, in the oldest group, it used to be that I was teaching most of the sessions, which is, you know, it has its positive, but it also has many negatives. I think it's great for students to see a variety of speakers who bring their expertise in different areas. They're not so bored. And so I'm lucky to have UCLA faculty and invited speakers from outside to come and teach a session or 2. I usually find that it works the best if it's at least 2 sessions in a row on the same topic so that you can put their interest. They can think for a week, digest a little bit the material, and then come back, and this works very well. So altogether, maybe 100 kids coming on a regular basis. In all of these groups, we try to include geometry as much as possible. So the question is, first of all, why do I think this is so important? If I were to know that we have so many geometry talks in this conference, so the grid presentation from Tatiana yesterday, the grid lab, right? This is geometry, right? The morning presentation for geometry of point methods via mechanics is again geometry. The challenge problem from Zvezda yesterday morning, another geometry problem. Elementary circles have their own geometry problems. Practically, I don't remember a single thing where geometry was not mentioned. But this is kind of focus on geometry. I asked children in the beginning of the year when they first came in, elementary school students, what do you think is mathematics? And I got a lot of different answers from them. It depended on their school experience and how broadly they understand the word mathematics. So I asked them to give me real life examples of what is mathematics. And basically you can classify their answers as dealing with numbers, basic algebraic sense, maybe even a little bit of probability, estimation, all of those, and very, very little geometry. Practically no one mentioned pictures from the elementary. I was wondering why. Well, because in school they thought that numbers is mathematics. And so I think the earlier you start telling them some other things, the better it is. So math is not just about numbers. The main thing is that you can show geometric pictures to very, very young age children. I'll show you examples of what we've done and get them thinking in ways they didn't think before. For young grades, partly helps us balance things better. It doesn't matter if you know multiplication table or not. If you're asked to see symmetry in a certain picture, or if you try to have another simple plane geometry. In school curriculum, I think geometry takes almost only 1 year. Am I right?
It's changing.
It's changing. In which direction?
It used to be high school, second year.
What's a parallelogram? What's a hexagon? That starts in kindergarten or first
Yes,
grade.
but yeah, I know that. But
Okay.
the thing is that this is not what I would call and what I would like to see as school geometry. I can tell you, maybe you already know this, that for example in Russia we studied geometry. Guess for how long? No, but no, special course in geometry, not mentioning that parallelogram is called parallelogram, but really rigorous geometry, starting from axioms, proving all the statements that triangles are equal if this and this is true. 5 years. There are many people here in the audience who will not let me lie. It's 5 years. 3 years you do plain geometry with all the axiomatics, all the proofs. This is standard school, not some special school for selected kids, for every single kid. They at least have to listen to proofs and try to get some ideas. And 2 years of 3-dimensional geometry. This is not done here at all. Yes?
Is it still the case?
Yes, it is still the case.
These are memories from...
No, this is still the case. Well, first of all, I'm not...
Because in Bulgaria it's not the case at all.
No, to my knowledge, it's still the case. Luckily, many things are changing for the worse, but this...
In my country, for
yes.
example, the influence rate is so huge that it changes.
Yes.
A few years ago, they were trying to do away with all geometry in schools in the Soviet Union. And then Vladimir Arnold went to the government and to the Academy of Sciences and made the point that it is so important for the development of logical thinking that they just got scared by him and left it alone.
Good, I didn't know about that. But another confirmation of how right this is. The thing is that geometry is really an ideal playground for children to explore. First of all, to make little discoveries. You can very often tell them, look at this and that and see what you observe. It's a perfect opportunity to start doing proofs by contradiction, and all sorts of other proof techniques. Wide range of topics. You can bring in children who are considered weak in mathematics because they didn't want to learn multiplication table or didn't want to learn adding fractions, and show them something beautiful and get their interest. However, of course, you have to take into account the foundation on which you're standing, and as we discussed, the foundation is weak. So you can take advantages of this, and I'm going to show how to take advantages. One way to take advantages is to take a topic which, for me, for my school, would be considered absolutely standard. No way that I would see this in a math circle in Russia. Here, it's a perfect math circle topic. But of course, you also have to do things which are just independent of school curriculum. So one way to include geometry is to just use it as a warm-up problem as often as possible. You don't have to have a whole session on geometry to include geometry. And this is also the way to collect information about to what extent your students are familiar with geometry. You give a 5-minute problem in the very beginning and you just see their reaction. And if you do this in the beginning of the school year, 2, 3, 4, 5 weeks in a row, you have enough information to plan several very successful geometry sessions later in the year, because you already know what their level is. They don't even know that you're probing them, but you can do it in all sorts of directions. So this problem is very simple for us. So you have a cube, points A and B, find the shortest path. I give this to all students from elementary to high school. I expect what? On the surface, yes. You can make up a story with this, but I'm not going into pedagogical techniques, just the material. So you can make up a story that's an ant that has to crawl and stay on the surface. And then if you want to explore, you can say that it's a mouse who is eating through the cheese, so she's allowed to go inside. Or it's just a cube which is made out of toothpicks, like in your presentations, and you can go on this. So this will be 3 different versions of the problem. But staying with just this version, even in high school, I get wrong answers for this. So I think it's important to see how they're thinking about that. they don't realize, they only go along the edges of the trial and error. So the idea that you can just unfold and look at the so-called net of the solid body is not natural to them. You can make it natural. Yes?
I wanted to say that the first idea is probably not to unfold it, but rather go, for example, from B to that to that corner across, and then from there to A along the edge.
That's one way.
It's not the shortest, but at least
Yes.
you don't have to unfold to see
Yes. So if they're in middle school, I don't give them away the answer. I make them come up with different ideas and compare what they have and then see why this works. In elementary school, I bring actual models and I make them measure what's going on. In high school, I expect them to use their brains a little bit more. Another warm-up type of problems which I think we've seen, there are some shapes, you need to cut them in half. This doesn't require any preparation, and sometimes they get it right away, sometimes not. So numerous problems with moving one match. So this is a house that looks this way, right? Make it look that way by moving just one match. If it's a new problem for you, it will take some non-trivial thinking to understand what's going on. You have a big square made out of matches, remove several, 4 or 8 or 6, so that you have 5 or 2 or 3 squares left. So there are big collections of these problems. You can find resources and make it a habit to use geometry warm-up problems. I'm going to show you a little bit more, but not too much, because we have to move on to other things away from the warm-ups. So here is another problem. You can you have 9 points. Use just 4 lines to go through all the points without lifting your pencil. You don't want to listen to me for too long, you can try doing this. I had another problem to give you to think about somewhere. Or put 12 stones into 6 rows so that there are 4 stones in a row. Children will tell you it's impossible, but then again, don't limit yourself. What are rows? Well, as long as they're on the line, that's a row for you, right? And so there are solutions for that which I will quickly show you. I have to rescale the time of my talk due to time constraints. So solutions can be like that, or like this, or like, I think, yeah, or like that. Or take a horseshoe and cut it into 6 pieces using just 2 lines. So first of all, if they draw as a model of horseshoe just a line in this shape, like a semicircle, they'll see it's impossible to do it. It has to have a thickness. So this is a way to do it.
So you can't move them after the first one.
A big source of such problems as Kardemsky, the Moscow puzzles. I'm trying to stick to resources available in English. This book certainly is. I think it has 259 wonderful problems. Not all of them are suitable for warm-ups, and not all of them are suitable for math circles, and sometimes you have to change the social context in which you present the problem, but it doesn't matter. Mathematical essence is there. And I think problems from this book were recycled many times in many different places. So here is another problem which you can think about. I'm not going to give the solution right away. It's non-problem, it's not my problem. It's maybe 20, maybe even more years old. Maybe you know it. So there is a regular hexagon divided into parallelograms any way that you like. You can have parallelograms of any sizes that you want, as small as possible, as large as possible. So because you have 3 sets of parallel sides, your parallelograms are going to end up being of 3 types in terms of directions of their sides, which I'll call red, blue, or purple. And prove that the areas, the total areas taken by red parallelograms, by blue parallelograms, and by purple parallelograms are the same, no matter how you divide into parallelograms. So that's not a warm-up problem, but it's a good problem to think about. So once you have some understanding of how much geometry your students know, or at least the directions that are, you can see from their responses to even simple problems like, not the last one, but the previous one, you can see what grabs their attention more, what's interesting, what will flow better, and try to build a geometry session out of this. So I have several things that I wanted to show to you, and maybe emphasizing that things done in elementary school can also be mathematics. Rigid motions of the plane is an excellent topic. Of course, if you're doing it at high school level, you should talk about the group of rigid motions. It's a perfect opportunity to introduce the notion of group, to show the non-commutativity and other wonderful properties. But if you want to do it at elementary level, so what I did in the session, I just said, okay, here's an arrow and here is an arrow. They are on the plane. How can you move one into the other? Of course, many different possibilities going something like this is a way, but then I asked, okay, can you do simpler than that? So they come to translation. Here they come to rotation. I found that it's difficult for them to recognize that this is a rotation. You have to show the center right away. Although they do get to this easily once they know that this is rotation.
They are different distances from the intersection point.
Yes, yes. I think I have it somewhere here. Yeah. So once they know about translation and rotation, you can ask them, okay, move this into this. So I have a session built out of this. I'm not showing you the entire session because this will take a long time, but just the ideas. And once you will agree with me that geometry is important and also doable in the math circle setting, you will take your favorite topics and present them to your students. Again, so for this, another possible answer is, of course, reflection, right? So some children tell me that this is not rotation, this is reflection. You have something in the middle, and you flip this to this side. So we discussed that it's impossible by this data from just this one picture to understand if it's rotation or if it's reflection. So we try to understand how can we distinguish. Well, we come up to this versus this. This being rotation, this being reflection with respect to the vertical line. This is all very doable, and if this is not mathematics, I don't know what is. You can do composition of rotations. You can make them observe that things don't commute if you change center. You can ask them, okay, so I have a triangle here, I have a triangle here. How can I move one into the other? What is the simplest way? Eventually they come to the idea that, okay, I'll try to get it as close as possible so that one vertex is the same, and then I will rotate, and if necessary, I will flip it to the other side. And that's partly your taste, how you do it. You can bring the physical objects, you can make them draw on paper. It depends on the group dynamics and your style and your personality. So as open as possible. So once you talk about rigid motions in high school, you cannot resist talking about other related issues. I mentioned the group of rigid motions. You can talk about inverse of each operation. You can talk about even spiral symmetry, where you rotate and increase the size. You can even talk about inversion, which is my favorite topic, reflection in a circle. Many wonderful things can be done with this. I think the session is described in Berkeley Math Circle's recent book. I have a session on my webpage devoted to inversion. Of course, symmetries, and you can even talk about what happens in 3D. Yes?
I have never tried to explain groups to high schools.
Say again?
I have never tried to explain the notion of groups to middle high schools.
Mm-hmm.
What do you think is the best way to tell them what a group is?
I had a speaker who did it via groups of symmetry with high school, but didn't do it in middle school yet. I'm not sure why, just didn't have a chance.
We've done it with elementary grades.
Mm-hmm.
Oh.
One way is with permutation groups, but you draw
Yep.
them like spiders, and you have them do, explore the Cayley tables of the creatures that you draw, which are basically the permutation groups, and they explore that. There's another one that's very simple. It's actually, someone mentioned equals earlier. There's an excellent activity in there for young kids about a stick robot. It's very simple. They have 3 commands: move one arm, move the other arm, or move both arms. And with this, you can feel it. So
I've done this for years and years. The classic way they do it doesn't work, which is given the axioms.
Well, it worked with me, so I don't know.
Well, that's the point. It doesn't work with kids. It's easier if you give them the field axioms, they'll understand better what a field is. But the notion of a group in some way needs to be tied to symmetry, which is where all these things go. And if you do it that way, a group of symmetries, and the axioms come later, as they did historically, by the way. The group wasn't, even Cayley's theorem, he didn't talk about groups the way we talked about groups. It wasn't until the early 1900s.
Okay, so the approach is projections. And
Yeah.
compositions of projections.
That's
Next one.
Yes.
I think that, Mark, I think that the symmetry group is group of symmetries are a little harder. It's better if you start with young kids. The easiest thing to start with are action groups. Like you have a soldier group. A soldier can turn left, turn right, or 180 degrees, and you can even grab a kid and
Yeah.
the kid shows that. Another excellent group is one sock group. You have one sock and you can put it, one action is you take it off and put it on the other foot. And that one more action, you take it off, turn it up inside out and put it back on the same foot. And the third one, of course, you take it off, put it inside out and put it on the other foot.
No, I use a similar idea to show just non-commutativity. First you put your socks on and then you put your shoes. Now try exchanging. I'm going to be as successful as you. I'm going to be happy.
So at what age do I understand that two groups are basically the same? That's what
They
you
are
start
not.
that's like.
They are not the same.
Yeah, that's why I'm asking at what
Yeah.
age? Give
I
us some
did it
idea.
in my circle and in Berkeley circle last month. And in both cases, they were middle school kids, and some of them were younger than middle school, and it went perfectly well.
So for example, I could say that what you're doing with the soldier and what happens with the socks is it's really kind of the same thing? Or?
No,
No, it doesn't
you
work.
come pretty soon. You come to the necessity of describing it somehow with a table, and then you see right away. You see that it's not the same.
Well, that's a more question. Yeah.
But also the notion of isomorphism.
Yeah, I mean, that's what I'm asking.
And it's lots of isomorphisms. And so I've worked out in a number of ways. By the way, a symmetry group comes also out of magic squares. Because if you start with magic squares, you can manipulate ways and so on. But another thing I do to get to isomorphism is lots of times there are two games that are isomorphic. A game isomorphism, and the strategies of one can be done in terms of the other. And that's due to their hearts.
So my question was, at what age do we abstract the group so that they actually recognize that there's something similar going on?
The groups is hard. The games is starting at grades 3rd and 4th grade. They can say the two games are the same.
Good.
Because
That's what I'm
Yeah, yeah,
That's
Once
what.
they play one, they start thinking of the other.
You've also done you've had a group actions. You've done an orbit stabilizer theorem using colorings on the balls of a square, just the vertices of a square, black, white, and make a chart showing which symmetries are preserved by which transformation, or which colorings are preserved by which transformations, and then look at that pattern. And you can get at the orbit stabilizer theorem by which is the
Yes. Let me try to continue. I'll probably go to an acceleration mode of some kind, and then you can stop me on as necessary basis. Extreme problems. Finding the shortest distance given some constraints. You can start with very, very early ages. So you need to go from here to here, visiting the river, to put out a fire or whatever, and then eventually they will come to this well-known solution. And once this is digested and understood properly, you can move on to more interesting things, which I'm not going to draw because I'm sure that you know what I'm talking about. You can go from here to here, visiting both of those. You can invent a story that goes with this. This is an example of extreme problems. A lot of high school kids did not see this ever. And this is so simple. You can test your audience, learn about it by doing this. I don't think you can go wrong, even with a brand new audience. You can, to recycle my warm-ups, you can move to finding shortest distances on 3D solids. So in elementary math circle, I make models of 3D circles, really 3D solids, really cut out everything out of cardboard or paper, glue it together, bring toothpicks, bring clay, and put together models, make their favorite polyhedron demonstrated to everyone else. By the way, we later investigate, count vertices, edges, and faces, make a big table, and eventually come to Euler's formula for polyhedra this way. So you can also use the same materials for completely different things, for several different things. Or for high school, do more general problems on maximization and minimization. An excellent book that has this section very carefully written and practically ready to take problems out is Courant and Robbins, What is Mathematics? It's probably, it's good for a lot of other things as well, but in particular for this one, so I wrote it here. I'm not going to talk about conic sections, which are, by the way, I think mentioned in school from what I know, but they still don't go through the properties properly. So if you take the optical property of ellipse, parabola, and hyperbola, this is a session right there. So I've done two-hour sessions on just this at a math camp. And this is very easy, and then eventually you ask them, so do you know what is the shape of the mirror in the headlight of your car? And they have to understand what it should be, use the optical properties, right? You want the light to reflect out of this focus and become parallel. Okay. Compass and ruler constructions. Nice topic, very well forgotten. Not almost, correct me if I'm wrong, because I'm actually curious to learn more about the school curriculum. It's practically not done in schools, right?
Constructions?
Yes.
High school it is.
Very little. I can hardly.
We can bisect an angle in this country. We can bisect an angle. We can draw a perpendicular bisector. That's about it.
Yeah. So this is on the left-hand side of my handout in the section basic. Two standard things like a common tangent to two circles. I tested this problem before preparing this presentation. I just asked my high school kids, including very strong kids who are going to AMI this week, to American Invitation. Have you seen this? No. Some of them did it after a lot of thinking. No, I have not seen this, and definitely not in school.
When you say ruler, is it a straight edge or the marks on it?
No, straight edge. Yeah, ruler is just a much shorter word, but then I noticed that you have to say it's a straight edge.
The ruler has marks on it.
Yeah, okay.
I guess you can prove it.
The value, I think there is a great value in construction problems. You can take them from any reasonable geometry book. For example, you can take Kisilov's book, which was translated. So take this book, recently translated by Alexander Giventhal, and find all sorts of construction problems there. And there is big value. It's the ancient book. It's translated into English very, very recently by Alexander Giventhal. And sold at Summers Dot.
Wow.
What?
It's with a U after S. It's not A.
What's
The name, it's S-U. Yeah.
Okay, well, thank you.
Is that?
So, no, I think it's called Geometry 1 and 3D Geometry translation. But in any case, and I think there is a big value in construction problems because you have to go through analysis. First, you have to imagine that your problem is solved, right? Then you have to understand how is it possible to come to this solution. You have to do the construction. Finally, you have to do the proof. No one is going to accept it unless you prove that your construction is valid. Just because it looks this way, there is no guarantee that it is this way. And of course, making a session or several sessions, just explaining to them what the doubling of a cube problem is, what is the trisection of an angle, what's squaring of a circle. Students don't know it. Explain it to them, and I think this is. You can do it again. It's your style. If you tell them right away that it's impossible, or if you want to make it some other way. Construction of a triangle given 3 bisectors is also impossible. Not so ancient, I think. So as I said, once you have your models of 3D solids, you can play with them and discover Early's formula. So this is just really how I make them. Do the table. They have 10, 12 polygons, polyhedra in the table, have vertices, faces, and edges, and then they look at it, and it's scary, because there are no patterns that you can see right away. So we start talking. Well, let's increase the number of vertices. What do you see? Is it true that the number of faces increases? Someone say, yes, for the first 3 examples it's true, but no, it's not true. And I think this is a little way for them to analyze data and eventually come to the discovery. So eventually they come to the right thing. And then if I do it in high school, I actually make them to do at least part of the proof. I tell them, okay, so you have a polyhedron. How can you make more? How can you make another one out of it? So there are 2 simple things you can do. You can build a tower over a given polyhedron. So let's say that you have this cube, add a vertex to it, build a new polyhedron, right? Clearly you can build another, you don't have to go over a square face, you can build it over any kind of face, and then see how this operation changes the things in the formula. If the formula was true, you build a roof, is it still true? I made the proof that yes, it's a simple proof, but it can be done. You can also do the opposite operation. You can cut the corner, so select a vertex, and then cut with a plane next to this vertex. Some of them see right away that these 2 things are opposite to each other. Some of them don't see it right away, and I'm okay with that. Eventually we come to it. Someone in the group realizes it. This is how it is. So this is very nicely described in Koya's book on mathematics and plausible reasoning, and I'm sure in many other places as well. I just want to point you to resources. And these are things that are just enjoyable to read, and I see many interesting things every time I turn to those resources and read them. So I think from this moment on, I'm just going to show you slides and not allowing you time to read them. We've done a session on surfaces with high school group. You can definitely talk about sphere, torus, several bagels stuck together. You can talk about Möbius strip, of course. You can show it even to elementary school kids. You can ask them to color it. That's already enough to see some interesting things. But with high school group, I've seen children who they're not successful in their school math, and they're not very strong in the math circle. But the pictures, gluing of the surfaces out of the models made sense to them. We didn't do the physical gluing, but taking a square and then gluing it in different ways allows you to obtain different surfaces like torus, sphere, plane model, projective plane. You can talk to them about these things. They will be able to understand it, and if you want to be ambitious, you can talk about early characteristics. We had a speaker who did this. I think it was very courageous. I don't think I would be able to pull it off so smoothly and nicely as this was done. And again, this is something that typically they wouldn't see for many years, but there is no reason for them not to take a glimpse out of this wonderful picture. Take a book on algebraic topology, and this is your resource. Of course, tailored to your students.
Shape of Space by Jeff Weeks. It's really excellent.
Okay. Yeah, I know lots of resources in Russian. That's why, but for this book I should.
The Shape of Space by Jeff
Shape
Weeks.
of Space. Okay, I can write it down. Shape of Space.
Shape of Space. Jeff Weeks.
So Shape of Space. Okay. I had a speaker in the high school group who was presenting notes, and just the idea of an invariant is a very powerful mathematical tool. kids. And then I've seen that this year Berkeley Elementary Math Circle did an activity where they started with graphs, simple graphs like this, and then they had a procedure to draw a graph, to draw a knot corresponding to the graph. So by putting crosses in the middle of every edge of the graph, and then connecting them to get a knot. This I think I didn't try it yet, but I'm dying to try it with my elementary school kids. These high school kids, I don't see any reason why you cannot explain to them that what knot diagrams are, why you cannot show them that two very different apparently knot diagrams can correspond to the same knot. Like this. This is clearly, think of it as a rope that is put in the form of a hook on the table, and then just pull it off. It's clearly just a circle. You can teach them about the Rademeister moves, the standard things. Or you can make them discover it. Again, it's your style. How you do it, it's different. I'm just showing you that I think it can be done and can be done nicely. And the idea is that there are such things as invariants is very powerful. I think you can, as you show it to them, this is pretty amazing. I always think, wow, so to prove the impossibility, I just prove that this very easily computable invariant, stick to easy things if you can. If they're not the same, then I started with different things. This is pretty powerful for that. Another thing which comes from standard school curriculum in many countries, but I didn't see it carefully done here. Just constructing in schools, just construct cross-section. So you have a cube, there are 3 points. The plane intersects the cube, draws the traces. What's going to happen? Why I thought of it is that because when I teach multivariable calculus at UCLA, I don't think I should continue. So, but they don't know how to do it, right?
Yeah, by unrolling it.
Well, not even by unrolling. Like here, you can try to draw the lines through x, y, staying in the same plane, and we know how to do it, right? The point is that it's teachable to the kids. So this line and this line are in the same plane, so they will intersect at some point, right? Which you can connect to this point. So you get the point of intersection here. You connect it like this. And then let's see, this line and this line are also in the same plane. So you get a point for yourself here and connect it to Z. And here's your cross section. It takes 2 hours in the math circle, at least, as high school kids to get at least to understanding of what are the trying to do. Depending on the kind of plane you're going to have different shapes, of course. So here's the topic right there. It's done in the handout on our web page. And you can do it differently. Okay, so I think I talked about 4 marks about building session, which is just geometry session. But there is another opportunity. You're doing something completely different. Pigeonhole principle really has nothing to do with geometry, right? One of the favorite topics in math circle. At the end, once they get the idea, maybe after several sessions, depending on the setup of your program, bring in a geometry problem which rolls around the same idea. So you've done pigeonhole principle, well then you can give them a problem like this. So you have a square of side 1, and someone throws 51 points inside of the square, show that there are 3 points that fit inside the circle of some radius. This is some geometry, some geometric context. You don't even have to mention to them that this is still, by the way, on our pigeonhole principle. Hopefully someone will realize that you need to cut up your big square into 25 squares. If you were to have only 50 points, then you wouldn't be able to say that there are 3 inside of the square, right? And then each square can be conveniently covered by a circle of appropriate radius. So you will have a circle of the radius that you need to have with 3 points in it. There are other problems of this type that I could show you, but I don't think we have time. Other topics, I'm not even moving to the next mode. I'm not even putting the slide up. So So there is projective geometry, and you can tie this to art nicely.
Show us.
No, but there is only list of topics. So you can do projective geometry. I had someone doing this for a couple of sessions with no handouts, just showing art and showing how to draw things in perspective. Big surprise for our students, since drawing is not part of standard curriculum, and drafting is not part of school
They
curriculum.
have computers, they have, they don't need.
I disagree with that. We can argue later, but you need to understand how things work. You can later go to a computer, but if you don't know what perspective is, there is a point of perspective from which this painting is drawn, then something is lost. Right?
No, I'm not saying that it's wrong to teach them that,
Yes.
but it's understandable why don't they know it.
Yeah. And last thing that I want to say is that there is more that you can, even more than you can do. I'm not even going to show my PowerPoint because of lack of time, but sometimes as you teach students more and more and they get to know you, they want to do some mathematics even more than in the math circle. So a year ago I had a math circle student at 12th grade come to me and say, I want to do some research. Okay, what do you want to do? He was not the strongest student that I've seen, but he's very persistent. He was not the strongest in the math circle setting, I should say. He was not an Olympian problem solver. He was not giving brilliancy solutions, shall we say. He was not going to USA Math Olympiad, but he wanted to do creative work. So I gave him a problem in geometry that I made up years ago to work on, and he made wonderful progress. I think geometry was one of the subjects where introduction was sufficiently easy, so I could explain to him what the problem is in 5 minutes. It's still an unknown thing. There are still some things published in plain geometry which are new. So if you're looking for an outlet of creativity of students and to do honest research, not modeled research in the math circle setting, really discover something new, this is a perfect opportunity. So he just gave a talk at an undergraduate conference because he's now a freshman. He's going to publish a paper. So I'm happy. In short, geometry is great, and the more the better. Thank you.